So just to what I will like to talk about is just to recap on our initial expectations for the quad booster. So the analysis, I've got an example of some analysis we have on the quad booster control system, and I'll also compare our model against what some of the initial results would indicate that we're getting from site. And then just to recap on the key learning points from today, so the things that we got wrong, things that we suggest for future deployments, etc. So obviously you've seen this quite a few times today. This is the circuit loadings on the 3 lines without the quad booster installed. And again, just to confirm that the down on market circuit reaches its firm capacity of 30 megawatts or 30 MVA when the export is around 54 megawatts. And you can see again that the Norfolk circuit is significantly lower than its rating. If we move now to this is what we've modelled the quad booster's impact at nominal tap. Obviously, when I talked through my example earlier, for most of you that were here, you may remember that I said the quad booster has no effect when it's on nominal tap. Obviously, that's in a perfect circuit, and the quad booster we have installed obviously has an impedance, as you've heard. And this impedance actually affects the power flows through the circuit. So this isn't actually, this difference or this change in power flows isn't a result of the tap or change in phase angle, but as a result of the impedance of the circuit, of the quad booster. That's one of the reasons for putting it into the Downham circuit as opposed to the Norfolk, because if we'd have put it into the Norfolk, whilst in theory it would have worked because we could have boosted the power in that circuit, we would have obviously put an impedance in there which would have made the problem worse at nominal tap. So what you can see from this graph is that the two circuit, the power flows through the down on market circuit and the Norfolk circuit are closer aligned, and that we can get around sort of 10 megawatts additional capacity without the need to change the phase angle at all. So the final graph that we have for our expectations is the quad booster at its optimal position, and you can note at this position the phase angle has been changed such that the loads through the down on market and Norfolk circuit are very, very similar, particularly at the higher end of the spectrum, which is where we would expect the tap changer or the quad booster to operate at tap 11. Towards the bottom of that, the 30 megawatts, the 20 megawatts, the 10 megawatts, we wouldn't expect the quad booster to be at tap 11 because it would just be unnecessary tapping and obviously reduce the life expectancy of the quad booster. And just to recap on sort of some of the measurements that we've obtained from site. So I mentioned earlier that the quad booster has spent most of its time at nominal position since it was put in place. Again, this is virtue of the control system that we've deployed, which is to exactly to deliver that. We don't want the quad boosters to tap unnecessarily. So the power flows through the two circuits, the down on market and the Norfolk, have been such that there has been no need to tap the quad booster, with only a few exceptions, which I'll go into in my next slide. Again, what you can see from here, the top graph being the modelled, what our expectations for the impact of the quad booster are, and the bottom one are based on measurements we've obtained from site. These are averaged measurements, again at the bottom, with the solid line being based on the actual data and the dotted line being based on projections based on this actual data. You can see that hopefully what you can see is that the proportion of power flows through the lines are very similar to what we expected them to be. Again, with the only noticeable difference is that the Suvry line appears to carry more load than what our models would suggest. Obviously, the net impact of that is that the load sharing between the 3 circuits is actually better than what we thought it was, and that with the net effect that, in theory, the down on market circuit could carry more load at this position. So moving on, just to give you an illustration of the operation of the control system. As I mentioned, there's been 4 tapping occurrences, both up and then back down again. And what we have here in the top graph is the power flow through the 3 circuits. I should note that these are 10-minute averaged data, and whilst the bottom graph is the deviation between the down on market circuit and the Norfolk circuit. Now, the objective of the control system is to ensure that this deviation doesn't exceed the upper and lower bandwidth, which are shown on the bottom graph in the red lines. And so what you can clearly see from this is that the power does never exceed those bandwidths, which is exactly what the control system is trying to achieve. And what you can see here, maybe not so clearly from the graph, is that a tap occurred on the 21st of September around midday. And at this point, you can see from the top graph that there was a significant change, step change in the power flows through the two circuits. And you can see to a certain degree that they are much closer aligned. Maybe what isn't so evident from this, though, is that the Sudbury circuit isn't actually carrying a lot of load. It's almost negligible load. And that's the main reason for the quad booster tapping in this scenario is because the Sudbury circuit isn't carrying any load, the Downham market and Needham market are carrying more load than what we would normally expect them to. And the second operation occurred on the 23rd of September, around midday again. What isn't evident from the bottom graph is that the deviation actually exceeded the upper threshold, met the upper threshold, which would initiate the tap. And the reason is because I mentioned that the data that we have is averaged over 10 minutes. And what you can see from the top graph is that at the time of the tap, the load on the Sudbury circuit actually significantly increases. So it's like the 10-minute averaging actually masks that. So what we've done, obviously, to overcome that loss of data, if you like, that we don't have available, is to check for the period between September and December, which is what we've analysed. We've ensured that we've analysed the Sudbury circuit to make sure there haven't been any significant step changes that would coincide with a deviation in the control system. And across the 3 months that we've analysed, the deviation never exceeds the upper or lower thresholds, and when it approaches that, it is tapped as it needed to. So obviously what we heard, just to recap on some of the learning that we had, obviously we heard that the quad booster was in fact boosting when it should have been bucking, which initiated for our modelling, initial modelling site. We've obviously since rectified that and understand why that occurred. And as I mentioned, and so did Satiris earlier, that for the next quad booster we would obviously look to address that via tests, and then ongoing from there it would just form part of our design review process. One thing that isn't clear, maybe I'll flick, actually I won't flick back through the graphs, but maybe it's something that wasn't so clear from my graphs, is that the optimal tap position is tap 11, and obviously what we would look to achieve maybe with future deployments of quad boosters is to have the optimum tap at, say, around tap 13 or so, which would give us a greater degree of control over the system. Obviously at the moment we have less degree of control, which isn't an issue per se. We still get the additional capacity that we expected to achieve, and we're still proving the concept of the quad booster, but obviously it's one of the key learning points we've identified for future deployments. And then just to recap on what I've just mentioned, the initial results that we're getting from site would indicate that the quad booster is sort of operating as we expect it to. We'll have, obviously, of course, over the next sort of 6 to 8 months, carry on undertaking trials, further measurements to understand and to verify the operation of the quad booster in its optimal position, to ensure that we're getting the loads are balanced as we expect them to, and that we can release the capacity that we expect to be able to release from the project. Again, one of the major points that we had, and I won't spend too much time on it, as we obviously just heard from Azam, but there was a significant amount of effort go into the development of the protection system. There wasn't previously a standard that we could just apply to the quad booster. It took a lot of effort, not to mention Alstom, from Carillion, from their commissioning engineers at EPS, obviously, and a number of other consultants and that we employed to address this issue. Obviously, we now have a system that fully meets all of our requirements. We didn't have to make any exceptions, deviations from standard industry requirements, which I think is quite an achievement, really, for the project. And so just to conclude, really, that our initial expectations or initial aim of the project was to produce or develop a quad booster that we could obviously deploy across or use at distribution level. So we feel that we've done that, we've achieved that to date. It's replicable at 33 and 132, so it's replicable elsewhere on the network. And obviously the systems are operating as they expected. We've had no maloperations. When the systems are expected to operate, they have operated, which would suggest that everything is operating as designed. And just to conclude, really, obviously the key learning that we've obtained from this project is applicable to all of future deployments. So the mistakes, people don't need to make the same mistakes that we've done. Hopefully that people take the learning that we've captured today, and if they need to deploy the quad booster on the distribution network, they could do so.